Alright guys, so here's a video of the study guide, which we've already started in class earlier, but we're going to go ahead and finish it here. But I'm just going to start from the beginning in case someone missed class or in case something didn't make sense there and you want to see it again. But if you obviously don't have to watch the whole video, you're just going to fast forward to the parts that you need. So let's go take a look here at study guide number 1. A table of selected values for the function f of x is given below. Use the table below to complete the statement. What is the limit of f of x as x approaches 0? Now, if we're approaching 0, then that means we have to approach it from the left and from the right. Okay? And the limit is the y value that we're approaching from the left and the right. And so from the right side, as you can see, we're getting closer and closer to about 0.5. And on the left side, we're also getting closer and closer to about 0.5. So since these two values are converging to a common number, we can go ahead and say that the limit is 0.5. So we'll take a look at number 2. A table of selected values for the function g of x is given below. Use the table above to circle the answer choice that best describes this limit. Let's see. So once again, we're trying to approach 0, and we're going to be doing it from the left, and we're going to be doing it from the right. Now, as I approach from the left with the y values, as you can see, the numbers are getting more and more negative, and they're not getting closer and closer to something. In fact, they're getting farther and farther apart. So, for instance, the distance between this number and this number is greater than the distance between this number and this number. So as we get closer and closer to our goal, those values are getting closer and closer together. But in this case, they're not. The distance from here to here is 90, and the distance from here to here is 900. So these numbers are getting farther and farther apart, which would indicate it's not really getting closer to anything at all. And if I were to approach from the right, the same thing is happening. So now, as I am going on the left side, you'll notice they're negative, so they're becoming more and more negative. So on the left side, we're approaching negative infinity is what's happening. As I get closer and closer to that middle value there, the numbers are just going to keep getting infinitely larger. And on the right side, they're just going to be getting infinitely larger. But it's different on the left and right. On the left, it's infinitely negative, and on the right, it's infinitely positive. And so in that case, that means the limit doesn't exist. Now, if both of these were positive, then here we could put an infinity sign. Or if they were both negative, then we could put a negative infinity sign. But when they're opposites, we just put doesn't exist. All right. Let's go ahead and move on to our next part here, number 3. A table of selected values for the function h of x is given below. Use the table above now to find each limit indicated below. All right. So we're approaching 0 from the left. So we're talking about this. What's the limit as we approach 0 from the left? Well, I'm getting closer and closer to, it looks like about 1.5 to me. And as I approach from the right, well, that's getting closer and closer to -2. Now, once again, if the left and the right don't match up, which they don't, then that means that the limit doesn't exist. But this one asks us something else. It says, what is h of 0? Now, h of 0 is the value that y actually equals when x equals 0. And in this case, it's 1.5. Now, if I were to ask that about the questions above, you would have to say undefined because there was no answer there. But in this case, there actually is a value for h of 0. All right, let's go ahead and take a look at questions 4 to 5 here. In questions 1 through 3, you were given the functions f, g, and h. Which of these functions is discontinuous? And give a reason for each of your answers. Well, actually, all of them are not continuous at their value of 0. So why are they not continuous? Well, this one's not continuous because f of 0 is undefined. Okay. Now, just to kind of review, before I jump into giving all the answers, there's three reasons why a function may not be continuous. The function may not be continuous at the given point. The limit may not exist at the given point. Or even though both of those things exist, it's possible that the function doesn't equal the limit, which is another requirement. So these are three reasons why a function may fail to be continuous at a given point. Now for this one, the limit did exist. Remember, for this one, we had a limit of 0.5. So the limit's there. The problem is the function doesn't exist at that point. There's no f of 0 value. Let's go ahead and take a look at number 2. For number 2, we had a limit that didn't exist. You remember we got the limit doesn't exist? So for this one, we could say that the limit as x approached 0, and this was the function g of x, did not exist. And by the way, when you're writing these things out, you got to be careful. Like I almost wrote f here, but we're talking about the function g. That is something that could cost you points. So you want to make sure that you are careful about that. And it's a really easy mistake to make, so just be kind of on your guard against that. Make sure you're using the right letters. Now, just so you guys know, you could also have said for this one that g of 0 doesn't exist, okay? Because as you guys can see here at x equals 0, there's no y value. So either one of those would be good answers. Let's go ahead and take a look at number 3. Now for number 3, h of 0 does exist. It's 1.5, so we can't say that the function doesn't exist. But we found that the limit didn't exist on this one, remember, because the limit from the left was 1.5 and the limit from the right was -2. So for this one, really the only good answer that you could give is that the limit as x approached 0 of h of x did not exist. Okay? And so none of those functions were continuous. And that's the reason for each of their discontinuities. Let's go ahead and take a look at number 5. In questions 1 through 3 above, you were given tables of 3 functions, f, g, and h. Which of these functions were most likely to have had a vertical asymptote? Now, a vertical asymptote is something that is vertical, a vertical line, okay? And as x approaches that vertical line, which we'll say is at C, as the line gets closer to that, the graph either shoots up into infinity or it could shoot down into infinity. It doesn't really matter, but the point is that as you get closer and closer to that value, the graph shoots off into infinity. So which one of our functions shot off into infinity? Well, as you guys might recall from question number 3, we didn't get any infinities here. We had actual limits on the left and right. And we didn't have any infinities on number 1 either. We had the same limit on the left and the right. The infinities were on number 2, the one where it just got bigger and bigger and bigger. And so the answer for this one would be number 2. All right, number 6. In questions 1 through 3 above, you were given the tables of f, g, and h again. Which of these functions has a removable discontinuity? Now, a removable discontinuity is one that even though the function is discontinuous, the limit exists. So even though we have a discontinuity, the limit actually exists. So which of the problems above, well, all of them were discontinuous, right? So check, that's one check off the board there. We have all of them were discontinuous, but now we need to narrow it down more. Which one of them had a limit that actually existed? And the answer was number 1. Number 1 had a limit because the left and right hand limits were both the same. And so the answer, number 6, would be number 1. All right, number 7. In questions 1 through 3 above, you were given tables of the functions f, g, and h. Which of these functions had a jump discontinuity? Well, other than the fact that we can now just know the answer by the process of elimination, it might be good to talk about how you can know it without elimination, because on the test, you're not going to have 3 tables like that. You're just going to have one, so you have to be able to recognize it. A jump discontinuity is one that looks like this. Okay? Now, when that happens, you actually have a limit from the left, and you actually have a limit from the right. But the problem is those limits from the left and right are not the same. Okay? Now, for number 1, that's not a jump discontinuity because the limits from the left and right were the same. For number 2, this is not a jump discontinuity because even though the limits on the left and right were different, they didn't exist. They were both infinities. The answer is number 3 because the limit from the left here was 1.5, so there actually is a left-handed limit of 1.5, and there's actually a right-handed limit also, but that one's -2. So even though both of the limits existed, they weren't the same. And therefore, number 7, the answer to that would be number 3. Or you could just say the table h of x. I wonder if that's probably what I should have been saying all along. But anyway, h of x is the one that has the jump discontinuity. That's because the limit from the left and the right existed, but they weren't the same. Okay? So just to kind of, you guys actually did pretty well on this on our quiz, so I'm not too worried about it. But just to summarize really quick here, how can you tell if it has a vertical asymptote? That's the one where you have infinities. How can you tell if it has a removable discontinuity? It's discontinuous and the limit exists. And how can you tell if it's a jump discontinuity? Because the limit from the left doesn't equal the limit from the right, but they both exist. Okay, and so that's how you can tell when you're looking at these types of discontinuities on a table. Okay, so let's move on to numbers 8 through 20 here. We're going to be finding some limits using graphs this time instead of tables. So the directions say that if a non-existent limit is an infinite limit, we want to be specific and say whether it's infinity or negative infinity. But if it's neither one of those things, we're just going to put it does not exist. Something that's kind of important to take note of is the fact that the j function has a vertical asymptote at 0 and a horizontal asymptote at 3. Okay, so the directions tell us that, so make sure you read your directions on your test so that you can catch those kinds of things. All right, so number 8 here. So you want to pay attention to 2 things up front. You want to look at what function you're using. I'm using the j function. And then you want to look at what x value you're approaching and what direction you're approaching it from. Now, since it's just 1, it doesn't have a little plus or a minus in the corner. That means I'm approaching an x value of 1 from the left and from the right. Okay, so let's find where x equals 1. So here's where x equals 1, and my graph is right there. So if I were to approach 1 from the left and the right, as you can see, those 2 arrows are joining up together at a common point. And that point, the y value of that point is the answer to our limit. So the y value there is 3. And so the limit of my j function as x approaches 1 is 3. Or in other words, as x approaches 1, y approaches 3. All right, let's go ahead and take a look at number 9. Now number 9, we're still using the j function, but this time I'm approaching 0, and I'm approaching it from the right. Now, x equals 0 is this vertical line right here. And if I'm approaching that vertical line from the right side of this graph, then as I approach that vertical line, I land at this point right here. And that's a y value of 2. Now number 10 is asking us to do the same thing, approach 0 for the j function, but this time we're doing it from the left. So if I were to approach this vertical line at x equals 0 from the left side, we run into a little problem because the graph never actually reaches a point. It just keeps going down farther and farther, and that's because there's a vertical asymptote there. So as x approaches 0 from the left, the y value gets lower and lower and lower indefinitely. And so for that, we're going to go ahead and put negative infinity. So for number 11, we are attempting to find the limit of j of x. So we're still on the j function as x approaches negative infinity. Now what that means is what y value are we approaching as we go left forever? Kind of a weird way of saying it. There it is. Why go left? Because x is approaching negative infinity. And x is a variable that tells you how far you're going to the left or how far you're going to the right. Well, if I'm going to negative infinity, that means I'm going to the left forever. Okay, so what y value are we approaching as I move along my graph to the left forever? Okay, so I'm going to start over here on the left side of my graph, and as I go to the left, follow my black line here. We skipped that spot, but we're just going to keep moving to the left forever. We're never going to stop. But what y value does it seem to be getting closer and closer to? Because of that horizontal asymptote, it's never going to cross it. So what y value is it going to getting closer and closer to? Well, it's getting closer and closer to a y value of 3, which is that horizontal asymptote. Now what if I change the question a little bit, though, and I say positive infinity? Well, that's asking the same question. It just means now we're going to the right forever. So I'm going to start on the right side of my graph now, and I'm just going to move along my graph. I'm going to skip that. And now as I go up, that arrow means that it never stops going up. So it's just going to keep going up. So what y value is it approaching? Well, it's not approaching anything, actually. It just keeps getting higher and higher. So the y value is going off into infinity. Okay? Let's go ahead and take a look at number 13. So this time we're going to be approaching negative 2. And since there's not a little plus or a minus in the top right corner of the negative 2, that means we're approaching negative 2 from the left and from the right. And they have to match if we get an answer. If they don't match, then there is no answer. So let's see how that's going to work out. So if I'm approaching, here's where x equals negative 2 is at this vertical line here. Okay? So if I'm approaching that vertical line from the left, and if I approach that vertical line from the right, the question is, are they meeting up at a common point? And they are. Even though that dot doesn't exist, they're still approaching that dot, and that's what a limit tells us. It doesn't tell us what the dot is. It tells us what dot we're approaching. And so we're approaching that dot there. And the y value, I would estimate that to be about 2.5. It's not a precise number, but we're going to guess about 2.5 would be the y value that we're approaching there. Let's go ahead and take a look at number 14. So for number 14, we want to find the limit of j of x times k of x. Now what that means is I need to find the limit of j of x as x approaches 2, and I also need to find the limit of k of x as x approaches 2, and then what I'm going to do is I'm going to multiply those two answers together. Okay? So let's go ahead and do that. The limit of j of x as x approaches 2. All right, so here's where x equals 2. And if I approach that line from the left and from the right, they are meeting up at a common point, which is at a y value of 4. So the limit of j of x as x approaches 2 is 4. Now you do the same thing for the k function. Here's where x equals 2. And as I approach from the left and from the right, once again, we're meeting at a common point there. And that common point is right there at the very tip. And that is a y value of 6. And 6 times 4 is 24. And so our final answer there will be 24. So the point of that exercise is basically when you have two functions being combined in some way, basically just find the limit of each function and do whatever operation they're asking you to do. All right, let's go ahead and take a look at number 15. Now this is not a limit. This is asking you what is the y value when x equals 4. In other words, I'm not asking you what is it approaching. I'm just asking you what is the actual y value at x equals 4. Well, for the j function, when x equals 4, the y value is 2, because that's where the solid dot is at. So I'm going to go ahead and put the answer in there as 2. But this is an important thing, because I think there's still a couple of folks out there that are a little bit confused on this. So the y value at 4 is 2, but the limit at 4 is 6. The limit is, as you approach from the left and right, what y value does the graph seem to be getting closer and closer to? But the y value is where the solid dot actually exists at. Okay, so let's go ahead and take a look at number 16 here. We want to know what is k of 0. In other words, what's the y value when x equals 0 on the k function? Well, there's only 2 dots on this graph where x could equal 0. But the problem is they're both open dots. So there is no answer for that. There is no y value for that point. Now there's a limit from the left. It is approaching a y value from the left. And it's also approaching a limit from the right. But the actual y value doesn't actually even exist. And actually, in this case, even though the limit from the left exists and the limit from the right exists, the limit overall doesn't exist, because in order for a limit to exist, the left and right-handed limits have to be the same. So let's go ahead and move on to number 17. Now the rest of these are composite functions. A composite function is when you have a function being plugged into another function. Now the main strategy I want to share with you when you're dealing with these things is to start by taking the limit that they give you, so I'm approaching 1, and you're actually going to apply that to the inner function. So you're going to take your limit and you're going to put it inside the parentheses with the k. So basically what we really want to do is we want to find what is the limit of the k of x function as x approaches 1. Well, here's where x equals 1. And so if I approach from the left or the right, we do meet up at a common point, which means the limit exists. And the limit exists right here at this point at a y value of 3. So the limit of k of x as x approaches 1, and that's whether you're approaching 3 from the right or the left, is 3. Okay? Now, looking at my j function now, where is x equal to 3? Well, that's right here. Now, whether you approach from the right or the left, that's also the same answer. So we both, either way, whether you're approaching from the right or the left, you end up with 5 as a final answer. So the answer to that one is 5. Okay? Let's go ahead and take a look at number 18. Now, once again, you're going to take the limit and you're going to apply it to the inner function. Now we answered this question a little bit earlier, and that question was, what y value am I approaching as we move to the left forever? And our answer was right here for this guy, and what we found was the answer was 3. Okay, so what is the value of k at x equals 3? Well, that's right there again. So we actually end up at a, oh, actually, that's incorrect, actually. Let me back up. That would be, at 3, we're right here, actually. And so that y value would be 4. Okay? So, let's go ahead and take a look at number 19. Number 19, we're asking, what is the limit as I approach -2 from the right of the composite function? And still, once again, we're going to apply that limit to the inner function. Now, I want to approach -2 from the right on the k function. So first of all, let's find -2. Here's the boundary for x equals -2. And if I'm approaching it from the right, then I'm approaching a value of 0 for the y. But now for this problem, it's kind of important that you pay attention where you're approaching that y value from. we're approaching it from the right in terms of x. But now since that's a y value, I'm approaching that y value of 0 from underneath of the 0, right? Which means that I'm approaching that 0 value from numbers that are less than 0. So I'm going to put a little negative there. Now, this is just another way of writing this. Okay? So this is a shorthand way that I made up, but I think I have seen some other mathematicians use it. But I just like to write it like this when I teach these types of problems. But if you have a 0 with a little negative inside, that's just the same thing as this. Okay? So now what's important though is that you understand that why there's a negative there. And that negative's there because I was approaching 0 from y values that are less than 0. And how do I know that? Because you're coming at the 0 value from underneath of it. Which means that for y values, that means less than. Okay? So that means we're approaching 0. Now when I switch over here to the j function, the 0 now is going to be thought of not as a y, but now it's going to be thought of as an x. So if you're approaching 0 from values that are less than 0 on the x-axis, that means you're approaching from the left now. So on the j function, we're approaching 0, which is this vertical line here, from the left. And I believe we answered that one earlier also. And what we found out for that one was that it was negative infinity. Okay? Let's go ahead and take a look at one more question. I believe it's kind of like a repeat of number 19, but just from a different angle. So, once again, the first step is you want to apply the limit to the inner function. So I'm going to take my limit, and I'm going to apply it to the k function inside the parentheses there. Now, if I'm approaching negative 2, which is here again, right? From the left, I'm still approaching 0, but this time, I'm approaching that y value of 0 from above it. So if you're approaching a y value of 0 from above it, that means you're coming at that y value from y values that are greater than 0. And so I'm going to put a little plus here. Now that's just another way of writing this. So since I'm approaching a y value of 0 from above, when we translate it to the j function and it becomes an x value, that means I'm approaching 0 from the right. So when I come over here to my j function, I'm going to find where x equals 0, and I'm going to approach that x value from the right. And in this case, I land at a value of 2. So the answer for that one would be 2. Okay? All right, so let's go ahead and move on and take a look at a couple more here. Number 21. Use j of x above to answer each question that follows. So we're only going to be looking at the j function for this part of the lesson. It says, where are the discontinuities, and explain why each one of them is a discontinuity. Well, discontinuity happens anytime you have a hole, gap, or jump. In other words, if I were tracing my function, anywhere where I would have to pick up my pencil is a place where we would have a discontinuity. So let's trace the function, starting from the left, tracing, and boop, we meet a discontinuity at x equals negative 2. So I'm going to write that down over here. And then we're going to keep tracing, and we reach a vertical asymptote, and I can't cross that line. So if I want to get to the rest of my graph, I would have to pick up my pencil again. So I have another discontinuity at x equals 0. So I'll pick up where I left off there, and boop, I got to pick up my pencil again, and that one is at x equals 4. And then we just kind of keep going. And after that, the arrow indicates there's nothing in my way, so there's no more discontinuity. It just keeps going after that. Now I have to give a reason why each one of these are a discontinuity. Now if you want to state the reason why there's a discontinuity, you have one of 3 options. One of your options could be that f of c doesn't exist. In other words, there is no y value at that point. There's no closed dot at that point. Another reason why the limit may, or the function may not be continuous is because the limit doesn't exist at that point. In other words, there's either a vertical asymptote there or the limit from the left and right don't match up. Okay? And then the third reason is, okay, maybe the function exists and maybe the limit exists, but even though those two things exist, the problem is that they're not the same. That would be another thing that would cause a discontinuity. So for each of those three discontinuities over there on the left, it has to be one of these reasons, okay? And the c value is the number that you have for each one. So, all right, let's go ahead and take a look at x equals -2. So let's start at the beginning. Does the function exist at that point? Well, the answer is no, because there's no solid dot. So we would say the reason this one fails is because f of -2 does not exist. The function doesn't exist at that point. How about at x equals 0? Well, for that one you actually have two. Well, actually, no, you don't. You only have one reason. You can't say the function doesn't exist at 0 because it does. There actually is a y value at 0. It's right there. It's 2. The problem is the limit doesn't exist. The line on the left and the line at the right are not converging and meeting up at one common point. So that means the limit doesn't exist. Finally, on number 4, the limit exists because the limit is 6. The function exists because the function's value is 2. But the problem is those aren't the same spot. And so that's another reason why there's a discontinuity there. And so that would be because f of 4, even though it exists, and the limit at 4, even though it exists, are not the same. And so those are your three reasons why a function may have a discontinuity at a given point. Now, number 21, part B, which you can't see yet, so give me a second. I'm going to clean up my graph real quick. Number 21, part B, asked a more specific question. So part A was, what are the discontinuities and where are they? Part B is, which of these discontinuities are removable? A removable discontinuity is one where the limit exists. So the limit exists here and the limit exists here. So the answer to part B would be, we have a removable discontinuity at -2, and we also have a removable discontinuity at 4. The only one that's not removable is the one at 0, because that's the one where the limit doesn't exist. Okay? Let's go ahead and keep chugging along. Number 22. Find the value of k that will make this piecewise function continuous. All right. Well, as we mentioned, for a function to be continuous, the function needs to exist at every point, and the limit needs to exist at every point. Okay? But now, first of all, sine and this function here, those are both continuous functions everywhere. They never have any holes, gaps, or jumps in them. If you're not knowing why that is, take a look at the sheet I gave you in 3.3 part 2, which tells you the continuity of various functions. And you'll see that both sine and linear functions, which is what those two functions are, both of those are continuous everywhere. So there's never any holes, gaps, or jumps. But something special happens with piecewise functions. Even though sine may be continuous, and even though 2x plus k, which is a straight line, may be continuous, the problem is if they don't meet up, then it's not continuous. So I need to make sure that they meet up. In other words, I need to make sure that, it's connecting them. I didn't want it to connect them. Let me try again. I'll draw it a different color. Maybe that'll help. There we go. I need to make sure that the straight line connects to the sine function. And the only way that's going to happen is if the limit from the left on the sine function and the limit from the right on the straight line function actually meet up at a common point that actually exists. Okay? Now, where are they meeting up at? Well, they're meeting up here at pi. If they're meeting up at all, they would have to meet up at pi. All right? So, I need to make sure then that the limit from the left of pi is equal to the limit from the right of pi. Now if I'm approaching pi from the left, I would be using sine of 2x. Why, you may ask? Well, if I'm approaching pi from the left, which is what that little negative there indicates, that means we're approaching pi from values of x that are less than pi. And so that means we would use the sine 2x. And if I'm approaching pi from the right, then I would use the other piece, which is 2x plus k. And I want to find the value of k that will make these two pieces connect. So I want these two limits to be equal. So I'm going to go ahead and plug in my pi to the sine. I'm going to plug in my pi to this function. And then we're going to solve for k. Now sine of 2 pi is 0. And if I want to solve for k, I just need to subtract the 2 pi on both sides. And there's my k value. So k would have to be negative 2 pi. All right. Let's go ahead and check out number 23. Now for 23 and 24, the directions tell us, explain why the function's not continuous at the indicated value of c. Now we've already done questions like this on the graph, but this time we're doing it with just equations. But remember, it's the same three criteria for a function to not be continuous. Either the function doesn't exist, the limit doesn't exist, or even though they both exist, the problem is that they're not the same. Those are three criteria that cause a function to not be continuous at a given point. So let's go ahead and take a look at this. First of all, does the function exist? In other words, am I allowed to plug this number into my function? Well, let's see. I end up with 1 minus 1 over 0, which is 0 over 0, and that is not allowed. So no, the function doesn't exist there. So we can actually just stop right here and say that f of negative 1 does not exist. And that's good enough, honestly. Okay? But just to kind of show you some alternatives there, let's see if the limit exists. Because the limit might actually exist. Now, you don't have to do this. I'm just kind of giving you extra information at this point because we've answered the question. Okay? But let's see if the limit exists. Does the limit, as x approaches negative 1, exist? Well, as you guys know, we can't do direct substitution. We've already tried that. But what can we do about this? We got 0 over 0, and that's a pretty clear indication that you're allowed to do L'Hopital's rule, isn't it? And now I can do direct substitution, which gives me negative 2. So the limit actually exists. This function does have a limit at that point, and it's negative 2. So the reason it's not continuous is not because the limit doesn't exist, because it does. By L'Hopital's rule, we can see that. But the problem is that the function doesn't exist. Okay? All right, let's go ahead and take a look at part B. For part B, trying direct substitution, once again, fails. If you try plugging in your 2, you just get does not exist. So, once again, f of 2 does not exist, and that's our reason. But for this one, let's just do the limit for the heck of it. And the reason I'm doing this extra work is because I'm not too sure what you guys are going to expect to see on your test. So it's possible you may end up with, one where you need to do the limit also. So I just want to make sure that I do both of these things. But if you find where the function doesn't exist, then just say it's done. That's fine. But anyway, back to this. Does the limit of this function exist as x approaches 2? Well, in this case, we've already tried direct substitution. It doesn't work. And in fact, you get 1 over 0. Now, that's not a L'Hopital problem. So we can't apply L'Hopital to this. I think I wrote my limit wrong. Let me fix that. Sorry. There we go. That's right. So we can't do L'Hopital. I also can't factor this because x minus 2 can't be factored, so I can't remove the discontinuity by factoring. There's no square roots, so I can't rationalize it. And it's not a complex fraction, so I can't simplify a complex fraction. Those are all the ways you could remove a discontinuity to get an answer. So this is actually a non-removable discontinuity, and when that happens, that means that the limit simply doesn't exist. So in this problem, you could say technically that, okay, the function doesn't exist, but you could also say that the limit doesn't exist either. Both of those are valid reasons for part B. Okay? Let's go ahead and take a look at part C. So in this case, we're looking at the point C equals 1. So that's where we have that hole, and there's also a solid dot below it. We've kind of already answered a question like this earlier, so this is a little bit repetitive. But why is this function not continuous? Is it because the function is not defined? No. The function is defined at 1 because there's a solid dot there. Is it because the limit doesn't exist? No, because the limit does exist. The limit is 1. Is it because the limit and the value are not the same? And the answer is yes. The function's value is -2, but the limit is 1. Those are not equal. So that would be the reason there's a discontinuity for that particular point. All right, let's go ahead and take a look at number 25. If p of x is a continuous function on the closed interval from 1 to 3, with p of 1 being less than or equal to k, which is less than or equal to p of 3, and c is on the closed interval of 1 to 3, then which of the following statements must be true? All right, so what this is kind of a convoluted version of the intermediate value theorem. Okay, so let's think about it a little bit. So we have a point at 1 and p of 1, and I don't know where p of 1 is, so I'm just going to put p of 1 there. And then at 3, we have another p-value. We'll just put that there, just making up points. And we want to know, is there a value in that closed interval from 1 to 3 where there's some value in between those that if you plugged in c to your p function, it would give you that y value. Okay? So which of these seem to kind of make that statement? This has nothing to do with the IVT. Now, this is actually a question I pulled from the an AP multiple choice test. The reason why those are even there is because there's other questions later on in the year where things that are worded similarly actually result in equations that look like that, but we're not there yet, so we know that that's way out of our ballpark there. That's not the answer. The IVT, the conclusion of the IVT just tells you that there is a C value. It doesn't tell you what C is. So it's not going to be E. It can't tell you what the C value actually is. It only tells you that there is at least one. It doesn't tell you there's only one. It tells you that there is at least one. So that's what the IVT does. It tells us that there's at least one value of C such that P of C equals K. All right? So that's forcing you to really think about the IVT because it is worded in a way that's different than the way I worded it in class, but the content is the same. So that's why it's important to understand these things rather than just memorize them. All right, let's go ahead and take a look at number 26 here. All right, so for number 26, we want to, this is an intermediate value question. We want to start by identifying our A value, our B value, and our K value. We next want to make sure that our function is continuous, which it is because it's just a linear function. And then we want to find out what is f of 5 and what is f of -1, f of A and f of B. And we can find those just by plugging in the numbers that they give us to the function. That one gives me -5. This one gives me 9. Then the final thing we want to do is we want to make sure that our K value is actually in between those two values. And sure enough, it is. So we're good to go ahead and make our statement So since f is continuous and goes from -5 to 9 on the interval -1 to 5, there must be some value such that f of that value gives me the k value I was interested in, which is -3. Let's go ahead and take a look at number 27. Selected values from the continuous function f of x are provided in the table below. What is the least number of times that f of x is equal to 4? All right. Well, if I go from 0 to 5 in the f of x, somewhere along the way, it must have crossed 4. And if I go from 5 to 3, once again, it would have to cross 4 again. And if I go from 3 to 9, it must cross 4 again. And then if I go from 9 to -8, it must cross 4 again. Okay, so in this case, there are 4 times that it would have to cross the value of 4 in order to get from one point to the other. All right. Now let's just say I threw another one on there. Let's say I put 12 up here, and for that one I put -5. Now in that case, if you're going from -8 to -5, you don't have to cross 4 to get from -8 to -5. So my answer would still be 4. Okay. So I just want to show you that it's not always the case that it's every time, right? There's some where it won't actually do it. Okay. Let's go ahead and get into some of the more calculation-based limit questions that we're going to be dealing with. All right, guys, so for the rest of the problems, we're just evaluating limits. All right, now I gave you guys this little handout that you see here on the right side of the screen, which helps you to just kind of know the process you're going to go through to find the limits at any time. Now I've broken it up into 2 kinds. One's where you're just plugging a number in, which is how to find a limit at x equals c, and then also ones where you're working with infinity, plugging infinity in. So limits at infinity, in other words. So we have 2 different charts here we're going to use, but basically we're always going to start with some direct substitution. Okay. Now if that doesn't work, then we have some options depending on what kind of a situation we're looking at. And here we have 1, 2, 3, 4, 5, 6 different situations that we want to be aware of. Now if you have a polynomial over a polynomial, you could either factor it and cancel and remove the discontinuity that way, or you can actually just use L'Hopital's rule. If you have a square root either in the numerator or denominator, then that's one where you have to rationalize it. If you have a complex fraction, then we need to simplify it. If you have a natural log, then more than likely, if direct substitution doesn't give us our answer, we're just going to end up doing L'Hopital's rule. And I just put an important little limit here that we might want to remember, that if you're approaching 0 from the right, it goes to -infinity. And I demonstrated that in my lesson with a graph, but you can also do it using approximations. Also, if you want to find the limit of e to the x, if direct substitution doesn't work, probably L'Hopital. And if you have a piecewise function, then you're going to find the limit from the left and the right. Now I put absolute value in here because, as you guys know, in this class, anytime we see an absolute value function, we're going to want to change it to a piecewise function anyway to find the limit from the left and the right. Now, if none of these strategies are either available to us or we've tried them and they don't work, then it's probably a non-removable discontinuity. And so the answer is either infinity, -infinity, or does not exist. And the way we're going to get it is just by plugging in a number really close to the desired value. And if it's a positive number, then that means it's approaching infinity. If it's a negative number, that means it's approaching -infinity. And if we're doing a double-sided limit and they don't match, then we're just going to say it does not exist. Okay. We also have a similar chart here for limits at infinity. So if we're approaching infinity, then we'll use this chart here. Okay, but most of it, for the most part, is L'Hopital. But we have some facts here about. I gave you guys a shortcut for working with polynomials where the power on the top is less than or equal to the power on the bottom. There's a nice little shortcut we can use. Otherwise, we're stuck with L'Hopital. And that's pretty much it. So these charts are going to help you guys with doing problems like 28 through 50 on the study guide and also on those types of problems on your test. So as you can see for number 28 here, I'm approaching a number, which means that we're finding a limit at x equals c, which means we're always going to try to do our direct substitution first. So the first thing I want to do is just say, well, hey, maybe it just happens to be continuous at that point. And if it is continuous at that point, then I can really just find the limit by plugging the number in. And let's see if that works. Okay. Well, cotangent, as you guys might know, is the reciprocal of tangent. So I'm just going to rewrite it as tangent. And tangent of pi over 4 is 1. So I'm left with negative 1 over 1, which is negative 1. And voila, we got an answer. So the answer, number 28, is 1. It was just a basic direct sub problem. Most problems, direct substitution is not going to work, but it's a good place to start. Let's go ahead and move on to number 2, or 29, I mean. So I'm approaching a number, so once again, we're finding a limit at c rather than infinity. And we're going to try direct substitution first, so here we go. Plugging in negative 3 to the top, I'm going to get negative 2, because negative 3 plus 1 is negative 2. And then plugging in negative 3 to the bottom, I'm going to get 9 plus 12, which is 21, plus 4 is 25. And that's a good answer. There's nothing wrong with that. So once again, that was another direct sub problem. The limit is simply negative 2 over 25. All right. Let's go ahead and move on to our next problem, number 30. So let's go ahead and plug in. So once again, I'm plugging in a number, and it's just direct sub. So if I plug it in, I get 4 on the top, and in the bottom, I'm going to get 9 minus 18 is negative 9, plus 9 is 0. And now we have a problem. Now we have a little bit of a problem. I can't do this one by direct substitution. So when direct substitution fails, we have to figure out which one of these situations, if any, it is. Now, in this case, it's a polynomial over a polynomial. So I could either do factoring or L'Hopital. Now, in this case, I can't do L'Hopital. Why not? Well, because I had 4 over 0. L'Hopital only works if you have 0 over 0 or infinity over infinity. And so the only thing I could try next is to factor. Now, I got bad news for you. If L'Hopital doesn't work for one of these, the factoring is not going to work either, but I'll just show it to you. If you factor the bottom here, you're going to end up with x minus 3 times x minus 3. And as you can see, nothing cancels out. And if nothing cancels out, well then, we really haven't removed any discontinuity. So, none of these other situations apply. This one's the only one that could have applied and failed. So if none of the above work, it's probably non-removable. So the best I'm going to be able to do is plug in a number that's really close to 3 and see what I get. It's either going to be a positive number or a negative. But I have to, since I'm finding the limit at 3, I'm not necessarily finding it from the right or the left, but it just says find the limit at 3. That means we need to do both. So I need to find the limit of this function as x approaches 3 from the left, and I also need to find the limit of this function as x approaches 3 from the right. Now, if we're approaching from the left, I want to plug in a number that is very small, but or very close to 3, but on the left. So I'm going to do 3 minus 0.001. And so if I plug that in, then basically what I'm doing is I'm plugging in 2.999 for x. And from there, we're just going to let our calculator do the work for us. And if we end up with a positive answer, well, then that would indicate that it's approaching positive infinity. So when I plugged this in, I ended up with a really big negative number. And what that means is that the limit is approaching negative infinity. So the limit from the left is negative infinity. But now we're going to do the same thing from the right. So now I want to plug in a number that is very close to 3, but on the right. So that means I'm going to plug in 3.001 for x. And we're going to see what we get this time. If it's also negative infinity, then we can say that the answer is negative infinity. But if it's positive infinity, well, then we're going to just have to say the limit does not exist. And sure enough, this one comes out to be positive infinity. Because when I plugged it in, I just got a negative number, or sorry, a positive number that was really big. So since the limit from the left and the right were different infinities, then we're going to say that this answer is simply does not exist. And once again, if they were both the same sign, then I would actually put negative infinity. Or if they were both if they were both positive infinity, then I'd put positive infinity. It just depends. But in this case, they were opposites, so it's no good. So we're done with number 30. Let's go ahead and move on to number 31. Let's go ahead and try. So once again, I'm finding a limit at a number. So we start with direct substitution. And plug that in really quick. So that's going to be, if I plug that in, it's going to be 2 times this, which is 6 pi over 4, which reduces to 3 pi over 2. Now, tangent of 3 pi over 2, that's undefined. So direct substitution fails. So let's see, it's not a polynomial over polynomial, so we can't do that. No square roots are involved. It's not a complex fraction. It's not any of these. Well, it's a non-removable discontinuity. So the only thing I'm going to be able to do here then at this point is to pick a number really close to 3 pi over 4 and plug it in. Now once again, we're going to have to do it from the left and from the right because it's not specifying which side to do. Alright, so I went ahead and jumped ahead a little bit here, but you take your 3 pi over 4, and if you're approaching from the left, then we're going to subtract 0.001 from 3 pi over 4, which is approximately 2.355. And if you're approaching from the right, you're going to add 0.001, which is approximately 2.357. I plug both of those in, and what I get for this one was a negative number. And so from the left, we're approaching negative infinity, and from the right, we're approaching positive infinity. And so once again, we have a does not exist situation. All right, let's go ahead and take a look at our next one then. So, the limit as I'm approaching -2 from the right. As you can see, direct substitution is going to give me a problem here. So, now we could factor this, but that doesn't really matter because nothing cancels even if I do factor it. I will show you. That's a difference of squares. So if you factor it, you get x plus 2 and x minus 2. So nothing cancels. So we're still kind of stuck with the same issue. So, well, direct sub didn't work, factoring didn't work, and none of these other things apply. So once again, we have a non-removable, and we're just going to plug it in. Now, luckily this time, I only have to do one from the right. Okay, so I'm going to take my c value of -2, and I'm going to add 0.001 to it. And that's going to give me -0.999. And that's what I'm going to go ahead and plug in for x here. Let's see what we get. So the result I get out of that is a negative number, and therefore we can assume it's going off into negative infinity on that side. At this point, you guys might be feeling a little overwhelmed, like, gosh, Bailey, this is a lot of stuff. So yeah, obviously your test isn't going to be this long. Your test will probably be 20 questions or less. I just wanted to give you as many questions as I could on your study guide. And you got quite a while to get the study guide knocked out. I just wanted you guys to have as many sample problems as possible because there is a lot of ground that we covered. Anyway, let's go ahead and take a look at number 33 here. Now it's a piecewise function. So when it comes to piecewise functions, what you need to do is you need to find the limit from the right and from the left. You're going to do direct substitution anyway, but you have to do the left and right-handed limits separately. So the limit as x approaches 1 from the left, in which case I would use this piece because that's where x is less than 1. And the limit as x approaches 1 from the right, which is this piece because that's where x is greater than 1, need to come out equal. If they're not equal, then the limit doesn't exist. So let's see what this turns out to be. That's going to give me 0. That's going to be -1 plus 6 is positive 5 minus 4. It's -4. Uh-oh. Those things are not equal, and therefore we would say, once again, that limit doesn't exist because the limits from the left and right aren't the same. If they are the same, then the limit does exist, but in this case, it does not. Let's go ahead and take a look-see at our next problem here. Another piecewise function. This one, though, they just want us to do 2 from the right. So if I'm going to find the limit as x approaches 2 from the right, all I need to do is use the part where x is greater than 2. We don't have to do both sides. And so we're definitely going to get an answer this time because it doesn't have to equal anything. So let's go ahead and do our direct sub. Let's plug it in there. I'll show my work this time. So that's -4 plus 8 minus 4, 0. Nice. There's our limit. So the limit from the right would be 0. Okay, a step function. Okay, now I didn't put that. I don't think I put these on our chart. Okay, but you guys might remember, so maybe add a little note here. Step functions, just draw an arrow to this because step functions are non-removable. So the only way to do it is by plugging in a value that's really close to the desired value. So I want to plug a number in that is bigger than 3, but only by a little bit. So I'm going to take my 3 and I'm going to add 0.001 to it, which gives me 3.001. And that's what I'm going to plug in here to this little equation. And that's going to give me -1.001. And remember, what does the step value function do? It rounds your function to the greatest integer that is less than this one. So the greatest integer that's less than this would be -2. Okay, and so that limit would be -2 from the right. Next one. All right, absolute value functions. Now, absolute value functions are really just piecewise functions. And so what we need to do is rewrite them as a piecewise function before we actually start finding the limit. So what we do is we take the part that's inside the absolute value bars there. We set it equal to 0. And we solve. And then we draw a number line. And then we're going to pick some values that are less than -1 and some values that are greater than -1. And we're going to plug those into our absolute value expression. And as you guys can see here, for the value on the left, that will change the signs. The absolute value will change that from a -1 into a +1. But for my value here on the right, there will not be a change. And so if I wanted to rewrite this as a piecewise function, then we're going to have 5x plus 5 over x plus 1 and then we're going to have 5x plus 5 again over x plus 1. And what we just discussed was how for all x less than -1, we'll change the sign. So we'll put a little negative in front of that one. And for all x greater than -1, we won't. Now, in case you haven't noticed, you're not actually allowed to plug in -1 here. So I'm not going to let either one of those things actually equal -1. Okay? So let's go ahead and continue here. So now what I want to do is I want to find the limit of this function from the left. So now that I've changed it, we're going to handle it like we would handle any piecewise function. You take the limit as x approaches -1 from the left. And if I'm approaching from the left, then I'm using this piece. Now, as you guys may notice, I'm not allowed to plug in -1. If you plug in -1, you're going to end up getting 0 over 0. Okay? Now, that means we could use L'Hopital. But it's a polynomial, so you could also factor. I'll do it both ways, and then you guys can just go the way that you prefer. Okay? But let's go ahead and see. So the first way I might handle it is by factoring, just because I like factoring. On the top here, I could take a 5 out. And that will actually allow me to remove the discontinuity. And that will leave me with a limit as x approaches -1 from the left of -5. And since it's just a constant, that's my answer. Now, another way you could do it is you could do L'Hopital. According to L'Hopital, since I got 0 over 0, this limit is equal to the limit as x approaches -1 from the left of the derivative of this, which is 5, over the derivative of this, which is 1, and we still have that negative in the front, and you still get the same answer. So it doesn't really matter whether you use factoring or L'Hopital. Anytime you have a polynomial where you end up with a 0 over 0 situation, either method works. They both give you the same answer. All right? So there's that. So that was kind of an interesting problem, because first of all, well, I don't know, maybe you're not thinking interesting, but first we had to change it to a piecewise. Then we did the rule for piecewise functions, but after that it really just became a polynomial problem. So there was a lot of limit stuff going on in that problem. All right, let's go ahead and take a look-see at another problem here, number 37. All right, direct sub. If I plug in -1, let's see what we get. I'm going to use an arrow because I'm thinking we're probably going to get a 0 over 0 here, but let's see. -1 squared is 1. -2 times -1 is going to be +2. Yep, so far I've got a 0 on the top. And then plug in the bottom, we got a 0. So yes, we do indeed have a L'Hopital situation. So therefore, we could say that this limit is equal to this limit, which by L'Hopital's rule would be the derivative of the top, which is 2x minus 2 over 1. Direct substitution is going to give me 2 times -1 minus 2 over 1, which is -4. Final answer. Now, this problem also could have been solved by factoring instead of using L'Hopital's rule, because it is a polynomial over a polynomial. Now, I'm not going to keep doing it in 2 different ways every time, but I just want to demonstrate you could go either way with this. I think I forgot my little negative in the front here, actually, though, so I need to go back and revise my answer. So since this is -4 and there's a negative in the front, that's actually going to end up being positive. But anyway, back to this problem here. You could factor that. On the top, and then remove the discontinuity, plug it in, and you get 4 that way as well. So it doesn't really matter whether you do L'Hopital or factoring when you have a polynomial over polynomial. So long as it gives you 0 over 0, you can do either strategy. Okay. All right, so that takes care of 37. Let's go ahead and take a look at 38. All right, now this is a complex fraction. First of all, direct substitution. Let's see if direct substitution works. I'm going to plug in 0 there. If I plug in 0 here, I end up with 1/2 minus 1/2, which is 0. So, therefore, by L'Hopital, I'm going to skip most of the writing there. I'm just going to say that this limit can be rewritten as, oh, you know what? I take it back. I take it back. We're not going to do L'Hopital here. I take it back. You could do L'Hopital, but it's not helpful, okay? L'Hopital would be very confusing, I think. And I just don't think it would actually clean up very nice. So what we talked about, if direct substitution doesn't work, since this one is a complex fraction, it's not a polynomial or a polynomial, I would not use the L'Hopital method, actually. I would just simplify the complex fraction. So what you're going to do is you're going to multiply everything by the denominator. And that way these cancel out. So now I have the limit as x approaches 0 of x times 2 plus x over 1 minus 2 plus x over 2. Multiply those together, you just get 2 plus x, right? Then we're going to multiply everything by 2 to cancel out that little 2. And that's going to leave me with the following. Okay, now, first we need to distribute this negative into the parentheses, which is going to cause this bottom piece here to become minus 2 minus x. Then the 2's, 2 minus 2 cancels. And then the x's cancel. And that's where the magic happens, because now I've just removed the discontinuity. Now I'm going to put a 1 there, because we can't have nothing in the bottom, but a negative, that'd be weird. So now we can go ahead and do our direct substitution. Plug that in. You get 2 plus 0 is 2, and 2 times 2 is 4, divided by negative 1 is negative 4. Okay? So with complex fractions, we simplify it. All right. So once again, I'm approaching a number, just like I have been for most of these problems. So that means we try direct substitution, but as you guys can see, direct substitution is not going to work. So what do we do in this case? Well, when you have a square root over a polynomial or vice versa, we're going to rationalize. Rationalizing is where you find the part that has a square root on it, and you're going to multiply that square root expression by itself, but with one little difference. You're going to have the opposite sign. It's called the conjugate. Whatever you do to the one side of the fraction, though, you have to do to the other. Now, the reason that we do this is because when you do this, there's a shortcut for multiplying conjugates. All you have to do is multiply the first two terms together to find out what your first term is going to be. And the square root of x times the square root of x is just x. And then you multiply your last two terms together. Negative 2 times positive 2 is negative 4. Now the bottom I'm going to leave as is. I'm sorry, the top I'm going to leave it as is, but the bottom is simplified. At that point, you should be able to remove your discontinuity. And then from there, you should be able to do some direct substitution. And we get 4. Okay? All right, so now we're switching gears here. Do you guys see what's different about this problem? We're approaching an infinity. And when you're approaching an infinity, we're going to have to change our little chart here. And instead of looking at how to find limits at x equals c, we want to talk about how to find limits at infinity. Now, The first thing we're going to do is we're going to decide, are we looking at a polynomial over a polynomial? This is the same thing here, but I had to be more specific and use letters. But this is still polynomial over polynomial. Is it trig, is it ln, or is it e? Well, it's polynomial over polynomial. So we have a nice little shortcut for these that I'm going to highly encourage you guys to use. If the power on the top is less than the power on the bottom, then the limit at positive infinity and negative infinity will always be 0. So as you notice here, this is a power of 1, this is a power of 2. So at infinity, the answer is just going to be 0. It's awesome. Okay, use the shortcut if you can. Okay, the alternative approach would be to actually plug in the infinity and work it out and see what you get. But you're just going to end up with an infinity over an infinity, and then you'd have to do L'Hopital, and then you plug in the infinity again. And that's a lot of work, so I'm discouraging you from trying that, but you could. Okay, let's look at another one. Here's another one where I'm approaching infinity, and once again, it's a polynomial over a polynomial. So in this case, the powers are equal. So what does this little thing here say? If the powers are equal, then the limit is the fraction that consists of the coefficients. So in this case, that would be 3 and 1. So the limit here would just be 3 over 1, which is just 3. All right, that's a shortcut. Gotta love them, use them when you can, because a lot of these problems do take quite a while. Now, when it comes to a situation like this, where the power on the top is greater than the power on the bottom, well, you're kind of stuck there. You actually have to take the long route and use L'Hopital. You're going to end up with either infinity or negative infinity. Okay, it's not going to have an actual real limit. So right there, we can boil it down to one of two possibilities. So you can put this, but the only downside is that, okay, you might save yourself some time by knowing it's positive infinity or negative infinity, but you know, if you just randomly pick, you're still not guaranteed you're going to get it right. So let's see if we know how to plug it in. So first of all, if I plug in my infinity, let's see. Well, infinity to the third power is infinity. Infinity squared is infinity. Times 2 is still infinity. And minus 1 is still infinity. So we end up with negative infinity over infinity. All right? And so that's a L'Hopital problem. We don't do factoring when it comes to limits at infinity. We only do L'Hopital's rule. So let's take the derivative of the top and the bottom. So we get 3x squared over 4x. Now, we can reduce that one, right? So let's reduce it. Save us a little bit of time if we reduce it. X goes into x squared x times, so we have 3x over 4. Now let's go ahead and do our direct substitution. We have 3 times infinity over 4. Well, that's infinity over 4, and infinity divided by 4 is infinity. So the answer is positive infinity. Actually, you know what? I'm wrong. I forgot about this. I always forget about that little negative right there. So that negative should have been there. It should have been there, there, and therefore the answer is actually negative infinity. Watch out for those little negatives. They're sneaky. I wish they would put them on the top, but they don't. They put it in front, so it's easy to forget. At least it is for me. So watch out for those negatives there. All right. So that's limits at infinity with rational expressions. Let's continue our journey. Now we're doing limits at infinity with exponential functions. So what we're going to do there is we're just going to do some direct sub, and if necessary, we'll do L'Hopital. Some things to remember for that is that at infinity, e to the x is infinity, and at negative infinity, e to the x is 0. So those are some good things to keep in mind. But let's go ahead and see what we can figure out. So I'm going to go ahead and plug in infinity here. That's going to give me e to the negative 3 times infinity. And when you take the limit of a constant, the constant just stays the same. So there's that. Now when you multiply a negative number times infinity, that will cause the infinity to become negative. And as we mentioned over here on this sheet, whenever you let e to the x go to negative infinity like that, it actually just becomes 0. And so the answer is 1. All right. Let's do another one here. So we're taking another limit at infinity, and it's an e to the x problem, so we're going to follow this route. We're going to start by doing direct sub. If necessary, we'll do L'Hopital, but we might not have to do that. Let's see. So let's go ahead and plug it in here. I'm going to end up with 4e over this. Now, a little while back, I gave you guys a rule to learn, and that rule was that anytime you have a number over infinity, it equals 0. Okay? And so what we really end up with here is e to the 0. And by the way, that it doesn't matter if it's positive or negative infinity, you still get 0. And anything to the 0 power is 1, and therefore this limit is 4. All right? So now we're going to do limits at infinity, but this time with trig functions. So let's go ahead and plug it in. So sine of infinity over infinity plus 4. Okay. Well, sine, when you take the limit of any trig function at infinity, it oscillates. And if you're dealing with sine or cosine, which we are, an oscillation over infinity just becomes 0. And so this one is also 4. All right. Let's go ahead and chug along and see what else we can discover here. So here I'm going to get negative infinity on top. And on the bottom, I'm going to have sine of negative infinity. There's a negative inside, but we're plugging in a negative infinity, so it actually just becomes positive. But that's okay. We just end up with an oscillation here on the bottom, and on the top we have an infinity. Okay. Now this one I didn't put on here. I don't think I did. No, here it is. Here it is. When you have an infinity on the top, and it doesn't matter whether it's positive or negative, an infinity being divided by an oscillation, we're going to say it doesn't exist. And the reason for that is because if we're oscillating, we're going back and forth between negatives and positives. And the infinity is causing it to get bigger and bigger as we do that. So what happens is the trig function causes your graph to go like this, but the infinity causes it to grow as we go. And so what happens is it just starts to go crazy after a while. And so it never really reaches any limit at all. All right, let's go ahead and take a look at number 47. Direct sub time. We're doing an infinite limit with an e function here, right? So e to the infinity is infinity. But there's a negative in front of that, so that's going to be negative infinity over infinity. And actually, back up a bit. I forgot something. I forgot about my 2. That's still there. We don't want to just ignore that. But anyway, like I said, that's going to be negative infinity. That's going to be infinity. And that's an indeterminate form. We don't know what that is. So that means we have to do L'Hopital. Okay? So, therefore, by L'Hopital, we're going to say that that limit is equal to the limit as x approaches infinity of negative e to the x. The derivative of e to the x is just e to the x, so that stays the same. And the derivative of the bottom is 2x. You don't take the derivative of this, you guys. Why not? Because I'm not applying the L'Hopital to this part. This part was not the 0 over 0, right? So that plus 2 is going to stay just the way it is. All right, so now let's plug in our infinities. So now I get negative e to the infinity over 2 times infinity plus 2. Well, got the same thing again, darn it. Which means we get to do L'Hopital again. So now I'm going to take the derivative again. Sometimes you got to do it more than once. So the derivative of e to the x is still e to the x. The derivative of 2x is 2. And that 2, we're not going to take the derivative of that because that's not part of our L'Hopital situation. This is the thing that gave us the indeterminate form, not this. So we're applying L'Hopital only to this piece. So we're not taking the derivative of the 2. Okay, now let's try again. This will be the last time, I promise. Plug it in here, you get e to the infinity over 2, which is negative infinity over 2. Now negative infinity divided by 2 is negative infinity. And if you add 2 to negative infinity, you get negative infinity. So the final answer there is negative infinity. All right, number 48. Let's do some direct sub. Two times infinity is infinity. E to the infinity is infinity. And infinity take away 5 is infinity. All right. Here we go. Got another trig one here. Let's plug in our infinity and see what shakes loose. All right, now we talked about this. A number over infinity is 0. So I have cosine of 0 on the bottom, and on the top, 2 times negative infinity is just negative infinity. Cosine of 0 is 1. So I've got negative infinity over 1, which is just negative infinity. All right, next one. Do our direct sub once again. One over infinity is 0. Cosine of 0 is 1. 1 times negative infinity is negative infinity. Right, next one. Let's try our direct substitution here. Now this is not at infinity, is it? So I'm going to take my little paper here and I'm going to scroll it back up to the top because now we're finding a limit at c. So we always start with our direct substitution, so I'm going to plug it in. And that is 0 over 0. So we're using arrows, not equal signs. Be careful with that. So therefore, by L'Hopital, we're dealing with an ln problem, right? So if you get an indeterminate form with ln, we're just going to use L'Hopital. That's pretty much all we got. So let's take the derivative of the top. The derivative of the top is 1. The derivative of the bottom is 1 over x. Now, you can simplify it first if you want to, but in this case, I don't think I really need to. We can actually just plug it right in, and all you're going to end up with is 1. So, there's my answer. All right, we're back to another limit at infinity, so I'm going to scroll down here. It's an ln problem, so we're going to be doing direct sub and probably L'Hopital. So let's go ahead and see how that pans out. Direct sub is going to be ln of infinity squared over ln of infinity plus 2 cubed. Okay, that's interesting. I'm going to use arrows here. Well, infinity squared is just infinity. And infinity plus 2 is infinity. And if you cube infinity, you get infinity. So what we really have here is this. Now, You might be really tempted to say the answer is 1 because those are identical, and anytime you divide something by itself, you get 1. However, you gotta be careful with that. The reason why is because the limit of ln at infinity is infinity. So that means that this is just another way of writing that. So this is actually infinity over infinity. So that means we really can't say it's 1. This is an indeterminate form. So we actually need to use L'Hopital on this. Okay? So if I were to use L'Hopital, the derivative of ln squared is going to be 1 over x squared times the derivative of the inside, which is 2x, over, now for the bottom, the derivative of this is going to be 1 over x plus 2 cubed times the derivative of the inside, which is 3 times x plus 2 squared. And the derivative of that inside is 1, so we don't really need to write it. So that's actually a double chain rule. Remember our little example we had where you have your yolk? You have the shell, and then you have, sorry, back up a little bit, and then you have the egg whites. So the derivative of the ln is 1 over x plus 2 cubed. The derivative of the green part is 3x plus 2 squared, just doing the power rule, moving the power to the front and taking 1 off the power. And the derivative of the yolk, the very inside, is just 1, so we don't really need to worry about that. But that's quite messy, so I kind of want to rewrite it a little bit. Let's see here. So if I put these together, this x is going to reduce with this x squared to give me 2 over x. So let's write that. And if I put these two things together, I'm going to have a 3 on the top. And this x plus 2 squared is going to reduce with this x plus 3 squared to leave only 1 x plus 3 on the bottom. All right. Now let's simplify this thing before we start plugging it in. I didn't simplify last time because I saw that it would be okay and I would get an answer, but I think this time if we don't simplify it, it's going to make it harder. Now this is a complex fraction at this point, isn't it? So what do we do with complex fractions? Well, we simplify them. So let's do that. So I'm going to multiply the top and the bottom by x plus 3. Which is going to give me that. And then I'm going to multiply the top and the bottom by x. So these cancel out, which leaves me with this. And then I'm ready to do my, oh, I forgot my x there on the bottom. Then I'm ready to go ahead and try my direct substitution here. I'm going to need some writing space, I see. I'm going to go ahead and distribute too. Why not? Why not? Let's make it a little bit simpler to look at. Okay. Now, if I plug in infinity, you guys, I'm just going to get infinity over infinity again. All right? Because 2 times infinity is infinity, and if you add 6 to it, you get infinity. And if you plug it into the bottom, 3 times infinity is also infinity. So we're still got infinity. So we got L'Hopital again. So therefore, by L'Hopital, we're going to say that the limit then as x approaches infinity is going to be the derivative of the top, which is 2, over the derivative of the bottom, which is 3. And since it's just a constant, that's your answer. Now, some of you guys might not have noticed this, but we have a rational expression, polynomials, where the top power equals the bottom power. And when that happens, the limit is just a fraction of the coefficients. So we could have used the shortcut on that too. But L'Hopital works. It's just that that's the longer way of doing it. Okay? So that problem was quite a problem. We had to do L'Hopital, and then it gave us a crazy looking expression, so we had to reduce it and simplify it. And even after that we got L'Hopital again, so we had to do it one more time to get our final answer. All right. Well, I think that does it. I don't think there's any more questions on this study guide here. So beyond that, there's a lot there, you guys. So have good notes, bring them with you on test day, and we'll see how things pan out for you. Till then, I'll see you guys later.